Have you ever wondered how our satellites revolve Earth in order to scout or research something from space? Did it cross your mind how fast was that satellite? How can it move freely in space without going out of course? Well, the answer in that is this. Uniform circular motion can be described as the motion of an object in a circle at a constant speed. As an object moves in a circle, it is constantly changing its direction. At all instances, the object is moving tangent to the circle.
But what do you mean by that?
Take a look at this example. The blue dot is not going out of orbit because it is constantly changing its direction and it only has a constant speed. This motion's net force is said to be inward or centripetal force. The time t it takes to complete a full revolution is known as the period. Now the first formula for UCM or uniform circular motion is getting the velocity. The formula for getting the velocity of uniform circular motion is velocity is equal to 2 pi r over t, where t is the time it takes to make a full revolution and r is the radius. Your time must also be in seconds per revolution. If not, you must first convert it before substituting it to the formula. The second formula is getting the acceleration by using this formula. Acceleration is equal to velocity squared over r, where r is the radius of the circle and v is the computed velocity in the first formula. Now here are some sample problems.
A satellite is said to be in geosynchronous orbit if it rotates around the Earth once every day. For the Earth, all satellites in geosynchronous orbit must rotate at a distance of 4.23 times 10 raised to 7 meters from the Earth's center. What is the magnitude of the acceleration felt by a geosynchronous satellite?
To get the acceleration you need to get the velocity first. But wait, the t or period is not given. To find t you must use what is in the problem, like 1 day, rev. Convert that to seconds/rev to come up to an answer 86,400 seconds/rev. Then substitute it to the formula of v. You should come up to this formula. Thus substitute again to the formula of acceleration to acquire this answer.
Problem 2. A 95 kilograms halfback makes a turn on the football field. The halfback sweeps out a path that is a portion of a circle with a radius of 12 meters. The halfback makes a quarter of a turn around the circle in 2.1 seconds. Determine the speed of the halfback and its acceleration.
Now this problem needs a little bit thinking skills. It says here that the halfback makes a quarter of turn around the circle. Now what does that mean? If you just substituted values you will probably get the wrong answer because you still need to multiply it by 1/4 because he didn't make a full turn around the circle. This understanding leads us to this solution. If you didn't get this portion correct you are bound to get the next one wrong because you need the speed to get the acceleration of the halfback. With that answer correct, the next solution should be this.
Now let us relate uniform circular motion with Newton's second law, which is the law of acceleration. Now let us use the formula F net is equal to m times a and the acceleration formula of UCM, which is a is equal to v squared over r. Then substitute a to v squared over r, giving us the formula for finding the tension, which is T is equal to mv squared over r. Now why do you think that this car is not falling off of its course? It is because of friction. That is why the car is still going in a circular motion without going out of its course. To find the minimum velocity of the car needed for it not to go off course is v minimum is equal to the square root of the static friction times gravity times the radius of the turn, and g is equal to 9.8 meter per second. Now let's say in this case it started to rain. Then after the rain this cool-looking driver decided to go uphill to burn some rubber. Why is the car not slipping or falling off? This is just like case 2, but an angle is given so that the car will not fall off the cliff. The formula for getting its minimum velocity is the square root of r times g times tangent of the angle. This is the velocity needed for the car not to fall off. Now in this example, let us say there is a person here leaning on a wall and is connected to a metal cord, and then the turbine started to spin. How is this person not falling off? Let us switch to the side view. The person is not falling off because of the friction in the walls. The formula now to find the minimum velocity for the person not to fall off is V minimum is equal to Rg over the static friction. In this last case, the scenario will be in a roller coaster. Take a look at this example. Most roller coaster have this loop right here. Now how does this cart made it through the loop? Since the weight is with the same axis with the net force, we can say that the weight is equal to mv squared over r, giving us the formula for finding the minimum velocity, which is V minimum is equal to the square root of r times g, and g is equal to 9.8 meters per second. Now here are some sample problems.
Bowser Jr. is on a time trial mode and he needs to drift his way to the finish line. The turns in the figure 8 track has a radius of 7.5 meters. What is the minimum velocity needed for Bowser Jr. to make a perfect turn and have a perfect lap? The coefficient of static friction is 5.555.
The given values are: r is equal to 7.5 meters. Static friction is equal to 5.555. G is constant, so it is 9.8 meters per second. Find the minimum velocity. After identifying the given, substitute to the formula in case 2 and you should come up with this solution. This lesson is not that hard. The key is just analyzing the problems and identifying the equation needed. That is all for now. Thank you for watching.